right, so just a little review before we continue. Just remembering for quantum mechanics in the atom that position and velocity of electrons are complementary, as well as the velocity of an electron is related to its kinetic energy, so thus position and energy of electrons are also complementary. The position of an electron can be described by a probability distribution map or a quantum mechanic probability distribution map. Basically, it's more likely to be in the center of the throw than it is going to be along the edges of the trajectory. So from now on, rather than try to describe precise locations or velocities of electrons, we will describe them as being in orbitals, because that is much easier to understand, and you guys are actually already familiar with orbitals from the last video, which is those n numbers, those spheres around a nucleus. Those are the orbitals. Or even with a simple atom map and you see the orbits going around the nucleus. So understanding the concept of orbitals will help us to understand how and why atoms form bonds to stick together. So we've been looking at atoms, now we get to understand how they can get bonded together. And just as a little reminder, little vocab, quantum mechanics is a terrifying but sometimes fun field of study that includes quantization of energy, wave-particle duality, and the Heisenberg uncertainty principle to describe it doesn't say here, but basically to describe how atoms interact with each other. The Schrodinger equation is this bad boy right here. Remember, this trident is the wave function. It is a mathematical function describing the wavelength nature of an electron. I have personally never really used this too much. I'm pretty sure I at least once have used the wave function, but I'm not actually sure. It's best to probably know it for now, but just know once you get out of general chemistry, I don't really see that often, but it's good to know and have in your notes just in general and at least know what it's trying to say. So then we got H, which is the Hamiltonian operator, a set of mathematical functions representing the total energy of the electron. This is a very complicated thing. You do not need to know. If it says a mathematical function, you probably don't need to know it, because again, I think I was just given the numbers for H in the wave function. And then the E is the actual value for the total energy of the electron, and we can actually calculate E with a different equation as well. So if you calculate the wave function squared, the solution gives you the probability density for an atomic orbital, or basically where are most of the electrons likely to be in the trajectory or the orbital itself. Unfortunately, when you solve for the wave function, you end up with many possible wave functions, and that's just probability. If you look at the trajectory distribution map from the last video, you'll understand what I mean. It's just like kind of everywhere along that trajectory, and you won't have to solve for the equation. I don't know what Gen Chem class is going to make you solve that equation. So solutions for the Schrodinger equation for the hydrogen atom. We're not going to solve this equation mathematically. Instead, we are going to describe the graphical representations of the orbitals, or how they're going to look when drawn out, that correspond to the wave functions. So we will see what these orbitals look like in section 2.6. Each electron in an atom can be individually described using 4 quantum numbers, and this is going to be really fun. It's going to be a little hard at first, but once you guys get it, you guys are going to be absolute pros, and it is going to look crazy once we actually start getting going. So we got n, which is the principal quantum number, which you guys are actually already familiar with. We've solved those n's from before. We got L, the angular momentum quantum number, or basically what type of orbital it is. Then we got M sub L, the magnetic quantum number, which is going to additionally tell us describe basically a little bit more about that orbital. And then we got MS, the spin quantum number, which is just saying, is an electron spinning up or is it spinning down? And we'll explain that more later. So the principal quantum number n, which is an integer or a whole number, so it's not going to be 1.1 or 1.5 or 1.05. It's always just going to be 1, 2, 3, 4, etc., just whole numbers that determines the overall size and energy of an orbital. So like these. So when we have here the nucleus, it has 1 proton in it for a hydrogen atom, and the electron is going around. A hydrogen atom will have an n of 1. Because there's only 1 orbital around it. So for a hydrogen or hydrogen-like atom, the energy of an electron is going to be this. So it's going to be this one right here. And if we have N2, then we're going to have this right here. So this is how this is going to be how we're going to calculate the energy right here. And we can even see a little chart here. N equals 1 is going to be this. N equals 2, 3, 4. And it's just putting these down here and squaring it. Next, we have the angular momentum quantum number, or L. It is also a whole number that describes the shape of the orbital. So there are 4 shapes that orbitals can take. There's an s orbital, a p orbital, a d orbital, and an f orbital. S orbitals are just circles. They're always just going to be circles. P orbitals, there's 3 types of p orbitals, and the range of these numbers is determined by the principal quantum number of the electron. These numbers range from 0, 1, 2. For an electron with n equals 3, the angular momentum quantum number can be 0, 1, or 2 because it is going to be n minus 1. So if n is 3, n minus 1 is 2, so L can be 0, 1, or 2. So for a p orbital, they're going to look like bow ties. They're going to be sideways, right up, and facing forwards and towards you. I think we'll be able to see what they look like a little bit further potentially. But that is what p orbitals are going to look like. And then it continues when L equals 2, so 0, 1, 2, we got d orbitals. And when L equals 3, or 0, 1, 2, 3, we got f orbitals. F orbitals are going to be the biggest and craziest orbitals. And I personally have never even really looked at f orbitals, so you don't have to worry about those too much, but you should be familiar with what they are. You're definitely gonna want to focus on s, p, and d orbitals. They have different shapes. Next, and again, we'll go back to these soon, so don't worry about that. But the magnetic quantum number, or m sub L, is an integer that describes the orientation of the orbital, and this depends on L, right? Because it got with that little L right there. So these numbers range from minus L to plus L, including 0. So if we have L equals 3, which is an f orbital, then the magnetic quantum number n sub L can be -3, -2, -1, 0, 1, 2, or 3. Keep in mind that all these quantum numbers, right? These are how we can find a specific electron in a specific orbital in an atom or in any element whatsoever. So that is what these quantum numbers are doing. So slowly but surely we're getting closer and closer. We're finding the right area, then we're finding the right orbital, then we're finding which part of the orbital it is. And with this one, we're going even deeper and we're seeing, is it the spin up electron or is it the spin down electron? It is the value that describes the orientation of the spin of the electron. Each electron has a spin up or spin down, and these numbers are either plus half or minus half. So spin up, up being positive, or minus half, minus being down, negative getting down, and positive going up. That's how I remember them. You don't have to worry about it too much, but basically the north and south poles are swapped from. I didn't really have to deal with that, but you just got to know that it's like plus half or minus half. Each specific combination of the first 3 quantum numbers specifies 1 atomic orbital. So each orbital can hold 2 electrons. These electrons are distinguished by the 4th quantum number. So as you get further from the nucleus, there's more space for orbitals. So when we're in the first shell, like hydrogen, where it only has like 1 proton and 1 electron, then that is going to be the closest to the nucleus, and it's going to be really small. That is their 1s orbital. Our m sub L is going to be 0, and our L is going to be 0, and our N is going to equal 1, right? And if you see these little boxes here, those boxes are going to be important. Each box can contain up to 2 electrons that spin up and spin down. That's why it's a plus half and a minus half. Think of it as clicking 1, therefore there's 2 electrons in that box usually, right? When we get to the second shell, or n equals 2, keep in mind that shells aren't going to necessarily mean circles. They're just meaning that shell contains the next set up of orbitals, which can all be different shapes. So when we have n equals 2, at 2 minus 1 is going to be 1. So we have L equals 0 and L equals 1. We have a 2s orbitals and our 2p orbitals. See, now we have room for 2p orbitals. We didn't have room when it was just 1s. Now we have ml equals 0, right? And ml equals -1, 0, and plus 1, because L equals 1 right here. And then the same thing when we get to the third shell, we'll have a 3s orbital, a 3p orbital, and now, because our shell is even bigger, it's getting further from the nucleus, we have d orbitals, right? And the energy is just going to keep going higher, because the electron's getting super upset. It's further away from the nucleus. It doesn't want to be far away from the nucleus, and so it's just getting higher and higher. Now, going to atomic spectroscopy, after becoming excited to a unstable higher energy level, the electron will return to a lower energy state, releasing a photon of light. So if we start here at n equals 1, it goes up to n equals 3, and it releases enough light to fall to a lower energy. Like I said in the last video, it will fall back down to a lower energy level, but it might not be the one that it started at, right? So here we have a little equation. This is very important. We have delta E, which is change. Whenever you see delta, that means change. It's just a shorthand word for it. So delta E is the change, or the energy of the photon release. It's the change in energy. And the change in energy, delta or change, is going to be the final of something minus the initial for something. So in this case, it's the energy of the electron in the final state, and it's the energy of the electron at the excited state. It's going to be final minus initial because usually final is going to be larger than initial, so we don't have those negative numbers, right? So right here, since the E of an electron, or the energy of an electron at a level n is this, right? Which we calculated from before, the change in energy is going to be this. So squared minus 1 over ni squared, or minus the initial. That's an I and an F right there. This should be a negative value since the energy of the electron is being decreased. The energy of a photon is the same with a positive value. So the energy of an atom equals the negative energy of a photon. Remember, a photon is that light that's getting released. What do we know if we know the energy of a photon? Well, if we know the energy of a photon, we know the energy of an atom, right? And we can take that further and we can find other things with the energy of the atom. So now we have this. Wavelength equals Planck's constant, which is 8. And remember, Planck's is spelled P-L-A-N-K. And it's going to be times c, which is the speed of light, right here, the 3.00 E8 meters per second. For an emitted photon, we can plug this E of the photon here to calculate the wavelength of light. So now if we know the E of the photon, we're gonna automatically be able to calculate and determine the wavelength. And if we know the wavelength, we can put it in the other equation and we can get the velocity of the electron as well, because we'll already know the mass of an electron. That's a given, right? So now all these equations are tying together, but take care not to get any of these equations confused, all right? So just an example, what is the wavelength of light emitted when an electron relaxes from the n equals 5 to the n equals 3 energy level? So well, we can keep going down here. We got our final minus initial here, so our 3 minus 5. We got them squared. We got this final answer of E. The change in energy of the electron is this minus this. And finally, we get to the subtracted amount here, which is the 1.55 e to the negative 19. I think this is supposed to be not... Oh, right. This is also supposed to be negative, this little square right here. So it's just saying that it got rid of the negative sign right here and made it positive, so we don't end up with a negative wavelength, because you can never have a negative wavelength. It's always going to be positive. So then it's going to give us an answer in meters, because remember, joules per seconds cancel out. Seconds up here with seconds, joules down here with joules up there. We're left with meters. That is what we want. However, we actually want nanometers, so you're going to have to convert this from meters to nanometers, and I highly suggest going and watch the previous videos if you forgot how to do that. So going over here, why is this only for hydrogen? There is a hydrogen energy transitions and radiation here. So a little question for you guys is trying to figure it out. Why does this look like that? It's kind of difficult to understand, but give it your best shot. Zoom in a little bit. Let me help you out there. Let me zoom in. Get a little zoom right here. We got 410, 434, 46, and 656 nanometers. So we're going from the blues into the reds right here. Or I guess the violets into the reds. These are the infrared wavelengths where we can't see them. These are the visible wavelengths, and UV wavelengths. We also can't see those. We got a nice little middle ground. But this specifically is for hydrogen. So is there something about hydrogen that's more unique than the other elements? Go ahead and try to figure that out. Next, we are going to go deeper into the shapes of atomic orbitals. I said we would come back here, and we are here now. So s orbitals, or L equals 0, it is the lowest energy state for an electron. It is the 1s orbital. That's important to note. The average position is at the nucleus, but electrons are never actually in the nucleus, right? Positions near the nucleus are likely, but this little chart here, they never actually reach 0. So for a 1s orbital, it's going to be spherish. We can look at it, and all the electrons are going to be in this little area here. So looking here, we got little nodes, right? The probability density versus the radial density. The probability density function is the probability per unit volume. It has a maximum at the nucleus and decreases with the increasing radius. So basically what it's saying here with these nodes is the further out you go, the less dense it's going to be, right? Because as we're really tight in here, just really close to the nucleus, all the electrons are going to be super attracted. But the further out you go, the less the electrons are affected by that positive nucleus, because remember, electrons are negative. And so the poles are going to be less strong, so they're not going to be as densely packed, as close together. They're trying to get right in there. They're less influenced by it, so they're going to be a little bit more widespread. The radial density measures the probability of finding an electron in a thin shell at distance r from the nucleus. So this radial density is 0 at the nucleus. So the radial density is also going to change depending on where you are. So the distance from the nucleus increases, right? We got a 1s, a 2s, a 3s, and this is what those s orbitals kind of look like, right? So L equals 0 means an s orbital. So these are our p orbitals. As I said before, they look like little bow ties. We got a px orbital right here. It says x right here. It is a px orbital because it is in the x plane, right? Think about a graph. This is the py orbital. It's because it's going up and down. This is the pz orbital. Think of it as facing towards you, right? Think of it's facing towards you in that way. This is going to be slightly different because they got x here, y here, and z straight up. So y isn't straight up, but z is straight up, so that's why it looks like this. If you want to make your graphs like that, you can. Just always label your lines so that way you know, okay? So this actually is going to tell us how many types there are. So for a p orbital, there's 3 domains, x, y, and z. So px, py, and pz. And when they're all together, they look like this weird thing. But when we get higher up, remember, m sub L is -1, 0, and +1, because p orbitals are L equals 1. That will tell us that there's 3. So the m sub L is actually telling us that there's 3 domains in there. So the x, y, and the z, which is actually pretty cool. So what do you think this looks like for 3 p orbitals right here? So we got 2 p orbitals. This is the distribution of it. So maybe try your hand at considering what a 3 p orbital would look a little bit closer. Will it look even more spread out? What do you guys think? Right here, we got xyz, 2px, 2py, 2pz, and we got the 3. If we notice 3px versus 2px, 3px is further from the nucleus, right? So it's going to be a lot bigger, a lot less dense, right? Just like s orbitals, 3p orbitals are further from the nucleus than 2p orbitals on average. Next, we got d orbitals. As we can see, n equals 3 for these, and L equals 2. If L equals 2, m sub L is -2, -1, 0, 1, and 2. That means there's 5 different types of d orbitals. There's d, yz, dxz, we have dyz, dxy, dxz, dx squared minus y squared, and dz squared. So if you see this gray box right here, imagine it cutting everything in half, and that's what plane it is on. So this is on the z plane, and it's cutting across the y. The dxy orbital is only on the x and y plane. The dxz orbital is only going to cut through z and x, right? It's going to cut it in half. We got our z and our x, and then x squared and y squared is also going to be on here, except instead of being perfectly diagonal in here, it is going to be perfectly on the line instead. So that is the difference between these two. And then we have this really weird dz squared orbital, which is going to have a donut ring in the center of it. So it's hard to imagine it a little bit, but try your best and make sure to take notes. I will zoom in a little bit so you guys can see it a little bit better, so you can pause if you needed. Alright, then going further, these are the f orbitals. Do not worry about these crazy names. I will zoom in for you if you would like to look at them closer, but do not even worry about these. You don't have to know them. Please, you don't have to. It's perfectly alright. You do not have to know those. But an f orbital is L equals 3, so that means we have 7 different types right here. So please don't worry about f orbitals at all. You do not need to know what those horrendous things look like. Just know that f orbitals exist. Alright, so once we put them all together, you can see that once all the d orbitals and the p orbitals are all stacked up, they look like a bunch of balloons inside of a balloon. They form basically a circle. Atoms are depicted as spheres because all the orbitals together make up a spherical shape. It's actually really cool, right? So whenever you're looking at atoms and you see that they're just circles, well, that's because all the orbitals where all the electrons are, remember, these orbitals are where the electron could be. So every single one of these balloons has electrons bouncing all over the surface of it, right? This is where electrons are more likely to be. These are little clouds of electrons in their own little respective areas, right? Atoms are kind of weird, but if you think of them maybe as balloons, it could actually help you a lot. And these balloons will always be able to fit or form a sphere shape. So I recommend going back through and looking at vocab words, things you don't understand, or other equations that we looked at, and definitely practicing with all these orbitals. So that way, if you see L equals 3, you're automatically like, I got it, that is an f orbital. And continuing with, like, remember, the n here doesn't really constitute the orbitals itself, but d orbitals are first seen in the 4th shell, so it might be, I'm pretty sure that's supposed to say f. F orbitals are only seen in the 4th shell. I don't know why that is. D orbitals are first seen in the 3rd shell, so that's supposed to say f right here. That's supposed to say f. Yeah, f orbitals are only seen first in the 4th shell because they're so big that they need the space in order to even exist. So know your n's, your l's, your m sub l's, and your spins ups and downs in the little boxes, right? Every single box is a type, so d orbitals will have 5 boxes that could each have 2 electrons in it. P orbitals can have 3 boxes. S orbitals can have 1 box that will have a spin up and a spin down electron in it. So keep that in mind and make sure to practice and drink some water, and you're gonna be okay. See you in the next one.